of JK flip-flop. You have already studied about the SR flip-flop and D flip-flop. So what is the need to study the next type of flip-flop, that is your third flip-flop? There must be some disadvantage in SR and D flip-flop. That's why we have to move to the JK flip-flop. And first of all, we will see what is that advantage that we are getting from the JK flip-flop. Then we will see the working of your JK flip-flop. So in D flip-flop, you already know that there is a single input, that is D. We call it the data input, and hence two possible combinations. But in SR flip-flop, I have made the truth table for SR flip-flop because we will use it for your JK flip-flop. And in this you can see there are two inputs and hence four possible combinations when your clock is high. So it is always good to have a 4 combinations as compared to 2 combinations, but there is one disadvantage in this. The last combination, when S is 1 and R is 1, is a not used state, so we don't use it. Okay, there is a contradiction that you have already seen in the SR flip-flop. So in this whole presentation, what we will try to do, we will try to make a flip-flop in which this 1 state is used. There is some usable form when we are having S as 1 and R as 1, and the flip-flop obtained is called as the JK flip-flop. So I hope it is now clear that why we have to study the JK flip-flop. Now let's move to the circuit for the JK flip-flop. This is the circuit for SR flip-flop, and we will try to make a JK flip-flop from this circuit only. Okay, so let's see what changes we have to do to get a JK flip-flop. There are two outputs to this, Q and Q complement. I will take Q from here, okay, and I will give this Q as one of the input to our NAND gate, the NAND gate in which R is one of the input. Similarly, I will take Q complement out and give it to the NAND gate in which S is acting as one of the input, like this. Okay, so this is our JK flip-flop. Okay, now I will write S as J and R as K. The next thing is the working of this flip-flop. So the first case is when clock is low, and you already know in this circuit when clock is low, at this point I'm having 1, and at this point also I'm having 1, and this is your NAND latch, NAND SR latch, you already know. And whenever the input to the NAND SR latch is 1 1, the output is stored, so I will call it memory state. Okay, very simple. The next thing is when clock is high and your J is 1 and K is 0. So there will be no change if you compare the truth table for SR flip-flop and JK flip-flop. The outputs are going to be same. So our Q is 1 and Q complement is 0. From here you can see. Now I will see the third case when clock is 1, our J is 0 and K is 1. Now from the SR truth table you can see that the value for output, that is your Q, is 0 and Q complement is 1. So till now you have seen that for the first 4 cases everything is same in JK flip-flop and SR flip-flop, but this last case is different and very important, so let's discuss it. In this, my clock is high, my J is 1 and my K is also 1. So what will be the values for your Q and Q complement, that we have to see. So before actually writing the values down, we have to do the analysis in this circuit, and for that I will assume Q as 0 and Q complement as 1. So let's write it down. Q is 0 and Q complement is 1. Now you can see that Q is given as one of the input to this gate and the value of Q is 0. So here I am having 0. My K is 1, you can see, so K is 1. Clock is also 1 always, and the Q complement is given as the input to this NAND gate and it is 1. So at this point I'm having 1, S is 1, clock is 1 again. Now we know how to operate with the NAND gate. First we have to take the AND operation for the 3 inputs, and then we have to complement it. So 1 and 1 and 1 is 1, and when we take the complement I'm having 0. So at this point I'm having 0, and 1 and 1 and 0 is 0. Taking the complement gives us 1. So for the NAND SR latch, I'm having inputs as 0 and 1, and you very well know that when this happens, the output is 1, 0. Okay, now you can see that the output is changed, so the input will also change. Q has become 1, so at this point instead of 0 I'm having 1. Q complement has become 0, so 1 will become 0 here. Now 1 and 1 and 1 will give us 1, and taking its complement I'm having 0 here, and 0 and 1 is 0, and taking its complement gives us 1. So this 0 will become 1. Now when this happens, we are having output as 0, 1. Similarly, if you do the analysis once again, you will find that at this point I'm having 1, this is 0, it will become 0 again, and it will become 1 again, and Q will be 1, Q complement will be 0. So there is one pattern you can see. The Q is changing from 0 to 1, 1 to 0, 0 to 1. It is actually racing very fast. So I can write it like Q is 0, 1, 0, 1 and so on. Q complement is 1, 0, 1, 0 and so on. It is racing, and a very important concept in the digital electronics. Let me write it down, important, because we are going to use it directly in our counters. And now what will be the output when this happens? You can see that when Q was 0, it will become 1, and when it is 1, it will become 0. So if I say Qn plus 1, that is my output here. If it is 0, it will become now 1, and again it will become 0. So it is actually the complement of the previous state. So whatever be the value for the Qn, we are having output as Qn complement. So this not used state is now Qn complement. This is we call as the toggling. There is difference between the toggling and racing that I will explain separately in one presentation. So this is all for this presentation, a very important one, and you have to remember this truth table. There is a slight difference from the SR truth table, in which the last state gives us Qn complement. We will use it for our excitation table and characteristic table in the next presentation.